We can actually check. We can see that one, but let's do the lecture, then we'll go and do the glasses later. Okay. Okay, so let's continue the discussion we had yesterday, the day before. We talked about the speed of sound and the definition of shock wave, the physical meaning of a shock wave, what the shock wave is, and how it is generated. The next thing we want to review essentially is the stagnation state. So as you all should be aware by now, a stagnation state is reached by decelerating a flow to rest isentropically, right, without any external work, which means that it should put to rest reversibly and adiabatically. It is also called the total state, and there are other names for it as well, but the total state is the naming convention we usually go with in this class. So like total temperature, total pressure, total of all properties. And then the question is, what is that? What is going to be the total entropy? Right? Because as I said, we have total pressure, total static pressure, temperature. Same thing goes on for all of them. But and all of them are different. But what's going to happen to the entropy? What is the difference between total and the static entropy? So look at the definition. We are putting the fluid to rest reversibly and adiabatically. What does that mean for entropy? It doesn't change, exactly. So essentially, your total entropy and static entropy are the same. There is no total definition for entropy. Entropy is always a stagnation property, if you will. Or it's never a stagnation property. Both of them are the same. So based on this definition, we can come up with a formula or a definition, if you will, for a total enthalpy. Total enthalpy is defined as your enthalpy plus the kinetic energy loss. Okay. If the fluid is moving at a speed v, velocity v, right, and we want to put the fluid to rest, the kinetic energy loss per unit mass. So all of the discussions are per unit mass, as we have discussed before. Per unit mass is going to be v squared over 2. So h of t is equal to h plus v squared over 2. And if we assume the gas is calorically perfect, then what is going to be the relationship between H and temperature? What does that mean? Calorically perfect gas are constant. And then we had a definition for H, which was equal to Cp multiplied by temperature, right? If your gas is calorically perfect, right? That was the definition. So if you plug that in, if you rearrange the formula, your ratio of the total temperature with the static temperature is going to be equals to 1 plus V squared over 2 CPT. Okay? Which, based on the formulas we have had for the speed of sound calculations, we can play with this a little bit and replace the second term on the right hand side of the equation with this term essentially. So your total temperature ratio to the static temperature is going to be 1 plus gamma minus 1 over 2 V squared over A squared, which is the speed of sound. And what is V over A? Mach number, right? So essentially you can relate your pressure ratios, temperature ratios, right? Temperature ratio at this point to the Mach number for a calorically perfect gas. That is very important, guys. We are doing all of this for a calorically perfect gas. in most courses that relates to fluid mechanics, you don't really care about that assumption because that assumption is always going to be valid. So in the propulsion course, since we may be dealing with the Mach numbers like 10, 20, whatever, right, very high Mach number, that assumption may be wrong at some point, and we will see that later today. Okay, so what can we do for the pressure ratios? Do we have any relationship that relates to temperature, any temperature ratio to any pressure ratio? The isentropic relationship, right? So you just plug this equation in the isentropic relationship. Your total pressure is essentially your second state pressure, and your static pressure is going to be your first state pressure, right? Instead of P2 over P1, we're going to get P of T over T, total pressure over static pressure. And just use the isentropic relationships, and you will have the total pressure ratio. We also have another relationship that relates density to the pressure ratio, density to pressure ratio, so we can use that to come up with the total density to the static density ratio as well. So, just a quick note before moving on, these four relationships are only true for calorically perfect gases, right? This is the only one that is based on definition, right? As long as you are in an isentropic process without any external work, this definition holds true, okay? So, let's look at the, as we see from these equations, all of these ratios, temperature, pressure, and density, relate to the Mach number, okay? So what's going to happen to these as you increase the Mach number? The pressure ratio is going to increase the most, then we have the density ratio, then we have the temperature ratio, and their distance is actually so much as you increase the Mach number that we have to plot this in a logarithmic plot, right? The pressure ratio increases much more. And why is that? It's pretty simple to explain. If you go back to the equations, you have this power here, which is always larger than 1, right? That's 1.4 divided by 0.4, right, for A. You're dealing for A. Well, it is always, it doesn't matter what kind of gas it is always larger than 1. So the pressure ratio is going to be higher. Then your power is going to be smaller for this case. The density ratio is lower, is going to be lower compared to the pressure ratio as you increase the Mach number. So we have it from Mach 0 to Mach 6. Essentially, we are covering the subsonic region, the sonic region, and supersonic, and also some hypersonic region as well, right? But what will happen if you increase the Mach number? As you can see, these are actually plotted with the formulas we already have. So these are not experimental results, right? And the pressure ratio, everything will, the increase is gonna become smaller and smaller. The rates of increase of the pressure ratio, okay? And we have, here we have up to Mach number 50, which is essentially higher than the speed you're gonna see when you are returning from moon, okay? But do these equations represent the pressure ratio correctly at the Mach 50? Okay? What do you guys think? No. Why?
You're trying to get more shock wave.
So, okay. Can you relate the shock waves to the equations we already have, or to the assumptions, right? The main assumption we had was that it is a calorically perfect gas, which means that Cp, Cv don't change in temperature, or constant, right? So how does that relate to? Yeah.
So the faster you go, the temperature is going to get hotter and hotter, so it will affect those values too.
Okay, you are on the right track. Yeah. So as you reach the hypersonic situation, something that you're going to see is the aerodynamic heating. Not only that, you're going to see a lot of molecular dissociation a lot of gas ionization, right? So you're going to have a lot of plasma formation there. And you are going to have a host of other chemical reactions. So essentially, it is not a good assumption with these situations present and the aerodynamic heating you're going to see. It is not a very good assumption. The calorific perfect gas assumption, it is not a good assumption. It is a very bad assumption. So you always have to be mindful of the limits of your assumption, especially when you are dealing with propulsion. Okay? So the pressure ratio equation we have, total versus static, the pressure ratio, temperature ratio, and the density ratio are valid up until some point, right? After that, if you want to relate the total pressure to the static pressure and total temperature to the static temperature and so on and so forth, you have to come up with another way. Okay, so you just have to be cautious with the data extrapolations. You cannot always extrapolate your data here, and it is very important in the propulsion course because we may be dealing with very higher speeds, right? Eventually. Is there any questions so far? Okay. So how can we deal with these cases where the calorific perfect gas is not valid? We have to use this HS diagram, which is the Muller. It is called the Muller diagram. And here we just have an introduction to this Muller diagram. So what happens is the definition of enthalpy is going to remain the same, right? That was the definition. We are assuming that even at a higher speed, we are dealing with the isentropic process, right? Because that was the definition of the total condition, right? So we are essentially, you have to use a combination of H and S. And the same definition we have for those states as far as you're dealing with total temperature applies. So you can actually find the total temperature if you have the total enthalpy, right? And then you go to the Gibbs equation, use the Gibbs equation to find the pressure ratios between the two states. Total pressure ratios or total temperature ratios between the two states. Is there any questions so far? As long as you have an idea on what to do, you should be all right, because this is just a review, right? You won't get any. Dealing with these type of problems is very challenging and hard, right? Just the couple of equations doesn't really help. So you won't see any problem. You won't get a problem out of this one, right? So you're going to deal with a calorific perfect gas always. Okay. And if you're dealing with an adiabatic process, your total temperature ratios are going to be, it's going to be 1, right? Because it's in an adiabatic process, the total temperature doesn't change, right? So we can find the formula for total pressures using the changes in entropy for between the two states, right? Just have to keep in mind that we are doing this between the two different states, right? If it was the if it was the PT over P static, then this would have been equal to 1, because this would have made sense at all. Does that make sense? So essentially, at higher speeds, you can find a relationship between two different states using the Gibbs equation that we already have, and also the definitions of enthalpy. And based on this equation, we can always conclude that in all adiabatic flows will result in a total of a loss in total pressure if you include the shocks, the frictional losses in the bilayer, and all of the other losses, which you have to when you are dealing with very high speeds, right? Is there any questions so far? So let's continue. The next part of the distribute chapter is going to focus on developing the equations we are going to use in this course here, the main governing equations. So far we are familiar with some definitions and concepts. We should be familiar with the main governing equations, right? But the next step is to essentially find the equations that apply to our case specifically. And our case is a case of a flow in duct flow, essentially. Flow inside the duct, right? Flow inside the duct with area variation. The area variation part of it is very important because we are always dealing with nozzles, diffusers, and so on and so forth, right? So flow inside the duct, doesn't matter if area varies or not, can safely be assumed to be one-dimensional. Okay? So essentially what it means is that you can safely assume that your flow is moving in only one direction. It doesn't move in the y direction, right? Or in the z direction, which simplifies the problem for us much, much more. Okay? What are the other assumptions we can make here? That's the principle, right? But yeah. It is compressible. It is. No, we are always dealing with compressibility. The compressibility part doesn't really come into play here. But so there is one main thing that you have to work on, right? You have to make sure that you are on the correct path here. And it's the viscosity. Okay? Can we assume that flow is viscous? Can we assume that flow is non-viscous, illicit, or do we have to bring in the viscous assumption? And then you're dealing with the viscous flow, you essentially have to deal with a lot of body analysis, right? Which makes it like 10 times more complicated. If you're dealing with one dimension, it's a regular, illicit, one-dimensional flow, it's going to be much simpler, right? So can we make that assumption here? That does mean I have to answer this better. That was my question. I'm going to go around the class and have all of your opinions, right? So essentially, I'm pretty sure you guys are familiar with the differences between the viscous and the illicit flows. Essentially, when you have a valve, you have to be mindful of that distinction always, right? Because of the boundary layer formation if the flow is viscous, right? Is this clear to everyone? Yes? Okay. So I just assume that we all know this. And if not, you can always ask questions, of course. Okay. What did I want to say? Okay, so essentially, if we want to assume that the flow, which is happening inside the duct, so we have a lot of valves, right, is inviscid, we have to make sure that we can show that the boundary layer doesn't separate from the valve, first of all. Second of all, the boundary layer is so thin that doesn't really affect the analysis of the flow inside the duct, right? Does that make sense? Okay. So do those conditions apply here or not? That's the main question.
It's a quasi, I think we can assume it's viscous.
We want to assume, so viscous is an assumption. Every flow is viscous, right? We want to assume it is not viscous, right? So we just have to make sure that it meets the two assumptions, the two things I just mentioned, right? The boundary layer is so thin that it doesn't really affect the flow that much, right? And the boundary layer doesn't separate from the wall. Okay. So does it meet those assumptions? first of all, you can just brainstorm, like Neerlef is contributing, you guys should contribute as well.
I want to say yes, but aren't there?
I mean, you have to elaborate, right?
Aren't there equations to determine whether, like, you found it after this case at university? Like, I want to say the Reynolds number of the flow mass to the boundary layer, so you can take what's coming in.
Reynolds number shows you that whether the flow is turbulence or not, right? Even if we talk about the viscosity, it contributes to viscosity, but it's a measure of the turbulence, right? Okay, exactly. So what is that flow? You're actually you are correct. You are measuring the right thing, but you are making the opposite conclusion, right? So when you have area, right, you go ahead.
I don't think it's right, but if your area changes when it's
We'll get to that conclusion. That's the next step, right? That's essentially your mass conservation, rho AB, right? Your area changes density constant, your velocity, right? But yeah. So onto the area change. When you have the area change, what's going to happen is that you're changing the velocity with the pressure gradients near the wall, right? And you're essentially pushing the flow, as long as pushing the boundary layer to stick to the wall, if that makes sense, right? But as long as you have a thin boundary layer, the separation doesn't really have a chance to play all that much, right? How can we have a very thin boundary layer?
Extremely high speed.
Extremely high speed. Are we dealing with extremely high speed in propulsion? Yes, of course, right? So it is very safe to assume that the flow is actually inviscid and is not viscous. Okay, but how can we derive the equations? That's the main step. The first thing you do is that you go back to this figure you have, that's arbitrary figure, flow is done. You just take one element of it and just try to analyze that specific element, right? That's the differential way of looking at things. And those of you who have had a class with me, you know that I love the differential way of looking at things, right? So we always do that. Okay, so it is a quasi one-dimensional flow. We're going to find the equations for that type of flow in a variable area done with inviscid fluid inside. And we have to apply the Taylor series to find this equation, but I'm just going to make it simpler a little bit. Assume that we have already done all of those. So the first thing you want to do is apply the conservation of mass principle. So whatever comes in goes out, right? There is no mass going out of these walls or coming in from these walls. These two represent the walls, right? So whatever is coming in is going out. What is coming in? What is the mass flow coming in? Is rho UA, right? Density, velocity, and the area. We assume at the outlet the density has changed a bit to rho plus 0, right? Which means that the flow is compressible. We didn't make any assumption as far as the incompressibility goes, right? And U has changed a bit, so U plus du. And area has also changed a bit. Okay. So you can just simplify this just by multiplying all of these together. You have to keep in mind that these differential elements, which means that there is small changes, right? When you multiply small changes together, like dp du, it's going to be even smaller, right? So you can simply neglect that, right? Does it make sense? Let's say your rho is 1, u is 1, this change is 0.1, right? 0.1 or 0.1 is 0.01. It's very, very small. You can just neglect that. So if you do that multiplication and then simplification, you will get to this version of the equation. You have to move everything to one side, you get rho u dA, UA d rho, and rho A du equals to 0. You divide everything by rho UA, what you're going to get is going to be dA over A, d rho over rho, du over u, right? Is there any questions so far? Okay. So we're going to get this type of equation, and this is the logarithmic derivative of the local mass flow rate. These type of equations are called the logarithmic derivatives, which also is going to tell you that your rho UA is going to always be constant at every slice of the duct, right? And also natural log of rho plus natural log of u plus natural log of A is always going to be constant. Okay? So that's the application of the conservation of mass. Let's apply the momentum equation. If you apply the momentum equation, this is the huge equation you're going to get. Then essentially we are dealing with the momentums and forces, right? The only force we have. What is the only force we have here? Flow inside the duct, right? It is air flowing inside the duct, so the gravitational force doesn't really matter that much, right? What is the only force we are going to get here? Pressure force, that's it, right? You always have the pressure force, that's the idea, right? And you can see the pressure force at the inlet and the outlet, and also the walls, because the pressure force is going to be applied to the wall as well. You can see on the right hand side, and on the left hand side, you can see the changes in momentum, right? So the first part is the rate of momentum out, rho UA, multiplied by the new velocity at the outset, essentially, minus rate of momentum in, equals to the pressure force, and pressure force at the inlet, essentially, and the opposite pressure force, and then be the second term, pressure force at the outlet, and then you have the pressure force at the walls. That's it. Okay. Of course, you can multiply everything together. You can simplify things. If there's two derivatives that are being multiplied by each other, you can just ignore them, neglect them. And eventually, this is the equation you are going to get. Rho UA du is equals to negative A dP. Notice that there is no derivative of area in this equation. So we can just drop the area from the two sides. Rho u du is equals to negative dP. The momentum equation, and we only have the momentum equation in one direction because we assume it's a one-dimensional flow, right? And this is going to be your momentum equation. So far we have two equations. We have the conservation of mass, and we also have the momentum equation. Is there anyone who can tell me why don't we call the conservation of mass continuity here? Because continuity equation is always considered to be the same as conservation of mass equation, right? That's exactly. So whenever you talk about the continuity equation, you are talking about an incompressible flow, which is not the topic of discussion here. Okay. So the next step is to find the energy equation for an adiabatic flow with no shaft work. We have already seen this in the previous lecture. Okay. Which is going to be equal to this. Changes in total enthalpy is going to be equal to changes in enthalpy plus U du. And there won't be any changes in total enthalpy when you are dealing with the adiabatic flow with no shaft work. And in a duct, you don't have any, in a duct that is not heated, you don't have any heat coming in, so adiabatic flow, and there is no shaft work on the dot. It's just a fluid flow. The next step, let's actually wait here. So we have the three main equations, okay? And what are the unknowns here? The goal here is to find a solution to this flow problem, right? That's the goal. So essentially, we have to have as many equations as unknowns, as the number of unknowns that we have, right? So what are the unknowns here? Pressure, temperature, area, and density, exactly, right? That's it. How many equations do we have so far? Just three. So we need another equation, and the equation we're going to use, and this is the equation you always use when you're dealing with compressible flows, is the equation of state. P equals to rho RT, right? And we can have a logarithmic derivative representation of that equation of state, which is going to be equals to this. This is going to be this equation. dP over P is equals to d rho over rho plus dt over t. And from the isentropic relationships, we also know that P over rho to the power gamma is always constant. So we can play with that a little bit and come up with a relationship between the dP over P and d rho over rho, right? We can always just plug these in and simplify the equation of state a little bit more, if you want it. So, I'm just going to give you some time to finish writing. Okay, so you're going to have four main equations: conservation of mass, conservation of momentum equation, energy equation, and equation of state. We talked about the unknowns. So, and we talked about the unknowns. You guys mentioned pressure, temperature, area, and density. But what about enthalpy? Is enthalpy an unknown here? Exactly. So we define, for a calorically perfect gas, we define enthalpy changes in enthalpy, and we are dealing with a calorically perfect gas here. Right? That is just a small part of the class that we did. We talked about the non-calorically perfect gases. We define changes in enthalpy to be equal to Cp multiplied by dT. And we can also have this relationship for pressure based on the definition of the speed of sound. And we're going to see why we find this relationship disappear just a bit later. Is there any questions here? So we have to go a little bit faster to be able to finish what I have in mind. But I have one question for you. What are the main parameters you work with when you are dealing with aerodynamics in general, internal or external? And we have mentioned internal aerodynamics is the topic of this class, right? What is one of the main parameters that we work with, variables we work with? The Mach number, right? The Mach that is related to the Mach. But none of these equations actually talk about the Mach number, right? So we want to find the equations using the Mach number. We want to find the area Mach number relationship. Okay. So from the equations from the previous page, we can have this relationship, right? Rho over d rho, u du is equals to negative. This is actually, let me just. Let's look at this momentum equation here. Rho u cu is equals to negative dp. If you divide that by d rho, you're gonna get rho over d rho u du, right? negative dp over d rho, and then this relationship is going to relate. You just take the derivative. The only things that are changing are p and rho, so we're going to get a relationship for dp over d rho, right? This is going to be here if you divide everything by d rho, right? Okay. So this is what you are going to get. Eventually, if you do a simplification and everything. Okay, just move things around a little bit. You're going to get d rho over rho equals to u du over a squared, right? So essentially this gives us a chance to replace d rho over rho with this in the logarithmic relationship we had before, right? The first one, the conservation, right? We're going to replace that phrase with the d rho over rho. And just plug that in. This is what you're going to get. And eventually, I really love to use the board, but I can't because of the online pickup. But that's all right. So we'll try to explain it here. What can we do with this u? Let's take it out. What's going to happen when you take this u out? You're going to get u squared du over au, right? Or you, I mean, you can say what's going to happen when you multiply everything by u. And you're going to get du, just regular du, right? If you play with it a little bit, you essentially u squared over au is going to be m squared, right? And you're going to end up with one remaining u in the denominator here. You can just take the m squared out. That makes sense. And this is what you eventually end up having. M squared minus 1 multiplied by du over u is equal to dA over A. Okay? So let's have a small discussion here. What's going to happen to this when you are in subsonic flows? Is it a positive or a negative value? Negative value. So what does it mean for this relationship? So you're going to have negative, whatever a negative value multiplied by du over u equals to dA over A. That essentially is going to mean that the positive changes in A is going to result in negative changes in decrease. Increase in A is going to result in decrease in U. Does it make sense? And the other way around. But what's going to happen when you're dealing with the supersonic conditions? It's going to be exactly positive changes in A is going to be increase. Increase in A is going to be meaning that you are increasing the U as well. So the diffuser and the nozzle is going to be different as far as the subsonic and the supersonic goes, because in a diffuser, in a subsonic regime should look like this, right? Because you want to have positive changes in A to be able to decrease the velocity. Does that make sense? So the goal of a diffuser is to decrease the velocity, right? And the goal of a nozzle is to increase the velocity, right? Negative changes in A, the velocity is going to increase. But since this relationship becomes positive, in the supersonic relationship, in the supersonic condition, your diffuser is going to look like a subsonic nozzle, right? So with this condition, you're going to get lower velocity coming out. Does it make sense? And so on and so forth. The same is true for the other one. The last thing we want to discuss is the sonic throat. Okay? Sonic throat is essentially happens when you're dealing with a combination of a nozzle and a diffuser. They're essentially what is called a convergent divergent nozzle, or a convergent divergent diffuser, right? So when, as I mentioned, when you're dealing with a nozzle, you want to increase the velocity, right? So let's say you're dealing with a convergent divergent duct, right? And a subsonic flow. What's going to happen is that, and you want to design it this way, right? That's the design. The sonic flow is a design decision. So you have to make sure that the area is in a way that you get Mach number 1 at the throat for this thing to work. Okay? So essentially, you have a flow coming in at Machs is smaller than 1. You design it in a way that you keep the area, you design the area in a way to get the Mach 1 at the throat, right? Because you have the equation, it's very simple. Just use that equation to find the area at this outlet, at the middle, at the throat essentially. And then you want to increase the Mach number at the exit. This is what you have to do, right? You go from the subsonic, flow comes in to a convergent, divergent nozzle, and goes up as a supersonic flow. Yes.
Can you explain why because I was reading over the summer that at the throat, like the maximum velocity could be is Mach 1, but all they related to was just because this equation can't be greater than that. Can you explain, like, from conceptual?
What was the question again? Sorry.
Why is the throat it can't exceed Mach 1?
Okay, what do you think that is the case?
I was always confused reading. I'm guessing just because it's going to be subsonic up to that point, and it converges until that point, and then it's supersonic.
So it is going to be a contradiction. It's not going to happen, right? So you're going to have some pushback from the other side. Does that make sense? So what you're asking about is that, actually, I have to use the word ask. Sorry, I'm on Peter. There is no other way. What you're asking is that, so that's actually why we call it the sonic throat, is that when you're coming in a Mach is smaller than 1, when you get to the point where Mach is equal to 1, you cannot go forward, right? That's it, right? That's what you're asking, right? Okay? And Ryan is asking why does it happen? That actually violates our equation, right? Our equation cannot go beyond this, right? That makes sense. So basically what it means that beyond this point, your implicit flow assumptions will not work, right? So beyond this point, your Mach number is not going to increase, right? Does it make sense? Your Mach number most probably is going to remain at 1, or you're going to get some backflow coming in, right? So this is going to be a throat, that your flow is on a throttle. You haven't had fluid dynamics, but if you had the fluid dynamics, in the fluid dynamics you would have seen the throttling condition and the nozzle diffuser things, right? It's essentially similar to that. Does it make sense? Yeah. Okay. So essentially, what is the physics we are dealing with? Essentially, it's not going to happen. It's a throat condition. And then we can also have a convergent divergent diffuser. As you can see, when you get a supersonic flow and transform it to a subsonic flow, right, as it goes up. Is there any questions here? So based on this, you can see in the convergent divergent cases, the sonic condition becomes very important to us, right? That's why we come up with this new condition. It's called the sonic condition, and we use the star superscript to identify those. Like P star, this is going to be essentially the pressure at the sonic condition, the static pressure at the sonic condition, the static temperature at the sonic condition, and also the speed of sound at the sonic condition. Okay? And then the final thing we want to do is to find the ratios between the total conditions and the sonic conditions and the static condition at the other points of the nozzle and the throat. Okay? That essentially these are going to give you some design ideas, right? If you know the inlet pressure, you can find the sonic pressure, area, and so on and so forth, right? Okay. Let's start with temperature. We had the temperature ratio, and for the between the static and the ratio between the total and the static temperature, right? We have this equation for it, right? We just solve it, and to find the sonic ratio, essentially, just you have to replace Mach with 1, right? Because of the sonic condition, Mach number is 1, right? And then you can essentially find the relationship between the total temperature and the sonic temperature, which is going to be simpler. Then just combine the two equations you have, right? Just essentially divide this equation by this equation, right? Does it make sense? To get the static pressure ratio with the sonic pressure ratio. So this is going to be your eventual temperature ratio, not the pressure ratio. Does this make sense? It's pretty simple to find the ratio between the total temperature and the sonic temperature at the throat. You are going to just put Mach equal to 1. This is going to be your equation. T squared multiplied by gamma plus 1 over 2. And then you have this whole equation that gives you the total temperature anywhere, right? And the regular the ratio between the static and total temperature anywhere, right? Just divide those two equations to find the ratio at the throat, temperature at the throat or the sonic condition, and the static temperature anywhere else. Then the question becomes, why can we do this, right? Because we are essentially comparing the total temperature at the inlet, for example, or anywhere, and the throat. And we are assuming those are equal, right? Why can we do this? Essentially because we are dealing with adiabatic conditions with no shaft work, right? You can assume the total temperature doesn't change, right? You can do the same analysis for pressures to find the total pressure, and also for the density. I guess we can just. So the only point I wanted to try to make with this calculations was that you are going to get your maximum flow rate at the sonic condition, but this is essentially going to be your maximum velocity at the sonic condition, because it's going to be your smallest area. Does it make sense? Okay. So this is going to be it for today. Thank you guys.